All right, so we talked about our different methods of evaluating algebraically. We plug it in, we factor, we multiply by the conjugate, or simplify complex fractions. The first two. The first one, we can just plug it in and it's totally fine. The second one, since we're plugging in 0, we cannot. So we factor out a greatest common factor, cancel, and find your answer once you plug it in. Now, just a side note here. If you are factoring and doing extra work, until you have plugged in the number, you need to keep your limit notation out here, okay? When you plug in the number, then we can lose the limit notation, just have our number, or like the numbers plugging in stuff, okay? All right, so if we take a look at down here. First off, can we plug it in this third one? No. So we kind of mentally go through our list of things. If you have a computer or an iPad out right now, put them away. This obviously not a factoring question, yeah? Yeah. Okay. All right, so what's our method here? Conjugate. First, what is the conjugate?
Root x plus 5 plus root 5?
Yes. So item number 1 is knowing what the heck you're multiplying by. Item number 2 is successfully being able to FOIL that out. So see if you can walk through finding the rest of this one. When I FOIL together the top, what is root x plus 5 times root x plus 5?
Root x, or x plus 5.
X plus 5. What did we discuss happens with the outer and the inner terms?
They cancel.
They cancel. So then I go straight to the last times the last, which gives me what?
Plus 5.
Minus 5. So once I have that, now what am I allowed to cancel?
The plus 5.
Okay, the 5s cancel first. Then the x's cancel. Now, I don't care if you show them in that order right there in one step, because I know we don't need to write a million things out. But just understand, the 5s must go first, then the x's can go, which leaves me what? Okay. All right, so now I have 1 over root x plus 5 plus root 5. I plug in 0 now, and what is root 5 plus root 5? 2 root 5. And that is as far as you need to go. Okay? All right, let's flip the page. Try another minute. We had a couple things about trig limits to talk about. This is the new stuff. This is not on your quiz that is coming Monday. I will not be here, but this is basically our review for our quiz. Okay? Trig limits will not be on there, to be clear. A couple things with trig limits. Okay? We are always going to try to simplify, possibly using identities first. And this is provided that plugging it in doesn't work. Okay, plugging it in is kind of always your first one. Secondly, we have 2 rules for trig limits, and these are called special trig limits. These are kind of like trig identities in that you know what they're equal to, and they are equal to that all the time. One of the special trig limits is this. The limit as x approaches 0 of sine x over x. There's nothing you can do to simplify that. And if you plug in 0 top and bottom, you're always going to get 0 over 0. But if you graph it in your calculator, you can see that the graph actually approaches a number, and that number is 1. So the limit of sine x over x as x approaches 0 is always 1. The second one involves cosine. That is the limit as x approaches 0 of 1 minus cosine x over x. And again, the same thing, if you plugged in 0, you would always get 0 over 0. We don't want that. There's no other way to fix it. But if you graphed this, you would see on the graph that this approaches 0 every time. Sine x over x turns into 1. 1 minus cosine x over x equals 0. Okay? Now, keep those in mind as we flip to the back of this page and quickly run through a couple trig limits. Review 1. What are we looking at here? Complex fractions. So let's review. Again, the first issue with this is actually knowing what to multiply by. What do I need to multiply by here? 2 and x plus 2. I must multiply that times both terms on the top as well as where? The bottom. Most of us get ourselves in trouble when we forget to multiply by the bottom. Okay? All right. Take a minute and see if you can finish that one out. So what happens here? What did we forget? The negative? That's often what it is. The x plus 2's cancel, which leaves me 2. The 2's cancel, which leaves me a negative 1 that I distribute to an x plus 2. So what will cancel next? First, the 2's. After I've canceled the 2's, then what am I allowed to cancel? The x's. But that leaves me what on top? A negative 1. So I have a negative 1 over a 2 and an x plus 2. If I now plug in 0, what do I get? Negative 1 over 4. All right, do we have any questions about that one? This is all just so far going back over what we did last class. All right, now we haven't really seen one like the next one with these little symbols in it, but have any of us seen these little symbols in other places? Yeah, this is delta x, yes? Now, for the purposes of pre-calc right now, all you need to understand is that x and delta x are two different variables, okay? If you're super uncomfortable with delta x and you want to like write over it and make it the letter y, you know, you totally could do that. It's so different from x that you could make it a y or something else, as long as it's just a variable. But I'm just gonna go back and keep it here to let us be a little comfortable with it here. So what do you think I can do here to simplify? I could take out the 3. I don't want to do that first, though.
Would you FOIL it?
I would FOIL it. So let's talk about what it would look like to FOIL x plus delta x times x plus delta x. What is x times x?
X squared.
X squared. Now, keeping in mind that x and delta x are two completely separate variables. What are the outer and inner terms going to make when you multiply them and put them together? 2x delta x or 2xy if you're using y's. And then finally, the last terms would be either delta x times delta x, or if you're putting those y's in place, y times y, which would give me delta x squared. Now I wrote that there so that I didn't have to show two different steps, because what do we still have to distribute to it? The 3. All right, so let's distribute the 3. That's going to give me a 3x squared plus a 6x delta x plus a 3 delta x squared. What is still on top that I have not written? Minus 3x squared. All right, so what happens from here? Yeah, the 3x squareds cancel. Okay, and then I have a greatest common factor. I can take out a delta x. Technically, I could also take out a 3, but I really don't care about the 3, do I? I really want to cancel that delta x on the bottom. So let us take out a greatest common factor of delta x. If I take out delta x, what am I going to be left with? 6x plus 3 delta x. So what's going to happen with my delta x's? Cancel. Now that the one on the bottom is gone, is it okay to plug in 0 for delta x? Yes, it is. If I put in 0 for delta x, what is going to be left? 6x. Now, whether it seems similar to you or not, there was one on the homework kind of like this. It was the ones with x's and h's. If you think about, I don't want to go out of this project right now on this because it will save it and then I will lose my recording stuff. But there was one on the back of the homework that had like x plus h squared minus x squared or something like that. So very similar to that kind of question. All right, now, we have not touched trig limits yet. Trig limits are pretty straightforward. They will require a small amount of use of your chart. because we never forget the chart. It's got to be, we know what the sine at 0 is, and we know what the cosine at 0 is, and all that. It will also require a small amount of identities, about the same, maybe less even, than what we used in solving. Okay? So on the first page, if you'll flip back with me. All right, so we are finding the limit as x approaches 0 of sine x over 4x. We just talked about a couple trig limits. Just to kind of go through my process here, I would initially think to myself, can I plug in 0? That would give me 0 on the bottom, which is the biggest problem, but also sine at 0 is also 0. So 0 over 0 is not good. Now, this should look to us a little bit like one of those special trig limits that we had on the front page. Which one does it look like? The first one. We had this rule on the first page. Equals 1. Okay, that was our special trig limit. What about this looks different? The 4. Now, I would never ask you to write this out in like these many steps. But essentially what you're doing when you do this is you are separating the number from the sine x over x. If I just separate the number, I can't just pull the 4 because it's on the bottom, right? It's really separating the fraction 1/4 from sine x over x. Does writing it that way change anything about the problem? No. Nope. And we know what the limit of this is according to our rules, right? That's 1. So if that's a 1/4 times a 1, what's our whole limit? 1/4. Don't make them super difficult. Okay? The one next to it is very, very similar, except it looks a little bit like the other one. We have a 7 times a 1 minus cosine theta over theta. What did we know that limit was? 0. So it's a 7 times a 0, which gives us 0. So trig limits are not really generally that difficult. Know a couple rules and a little bit of plugging in using our chart, and we will be good. Now, let's take a look at this one. We're going to use a little bit of identities on it. This one, to me, once I look at it, looks a little bit like the first and a little bit like the second. Okay, I've got a 1 minus cosine squared, which is not quite what I have on that one. And I've got a sine x and an x on the bottom. Are there any trig identities we could use to help us simplify? 1 minus cosine squared changes into sine squared. All right, so my initial step is to change that into sine squared. Now, do you remember how I told you on that one just above, we essentially took that 1/4 and the sine x over x and kind of like split it up? We're going to do the exact same thing on this. Sine squared really means a sine multiplied by a sine, right? So, first, what am I allowed to do with one of my sines? Cancel it. So you could either split it into 2 pieces and cancel it, or you could cancel it the way it is here and just say, oh, this has now turned into sine x over x, which we know from our special trig limits is equal to 1. So many of them turn into our special trig limits. Others, we just have to plug in. Our last 2 examples are on the back. All right, we got a tangent. Do we have anything in our special trig limits that look like tangents? No. Nope. We do have things on our special trig limits that look like what? Sines and cosines. So what do we know about tangent? It's sine over cosine. So let's start there. We have the limit as x approaches 0, and I'm going to change my tangent out for sine over cosine. Now, just because I know where I'm headed next, I'm going to write that x as x over 1. What do we usually do with double fractions? We flip them. Flip and multiply. So just like that one where I took the 1/4 and separated it from the sine x over x, I now have 2 separate fractions, sine over cosine, which is now multiplied by 1 over x. Now, do you see within that, even though they're separate fractions, remember in fractions, if you multiply the tops, multiply the bottoms, it makes like one big fraction? Do you see kind of the pieces of one of the trig limits? I have a sine x on top, and I have a x on the other side, on the bottom. Am I doing anything wrong if I switch these two? Like if I put the x underneath the sine, and if I put the cosine under the 1, have I actually changed anything? No, I haven't. Because you can multiply in any order that you want. If that messes with your head, think about it. 2 times 3 times 4 would be the same as 2 times 4 times 3, right? No matter what order I multiply them in, I'm going to get the same answer. So, same idea there. I am perfectly fine saying that I can just go ahead and switch the x and the cosine. Okay? So this becomes that. Now, if you don't need to actually write it that way to see what we're doing, feel free. Don't worry about it. But what do we know the limit of sine x over x is? 1. And then my second question is this. I have a 1 over a cosine. But is there any problem with plugging in 0 to cosine? No. What is the cosine at 0? 1. So 1 over 1 is another 1. And 1 times 1 gives me 1. Lovely. Last but not least.
Can you explain
Yeah.
the denominator switch again?
Yep. Essentially, what you can think about it is if you're multiplying two fractions together, they really just become one fraction. So that's like a sine x over an x cosine x. So then I have my sine x over x. But this cosine still has to have something on top of it. So it's like there's just that 1 there that we kind of combined with the sine. You can take the pieces of fractions and put them in pieces, or if it makes sense to explain it this way. Let's say I was multiplying 3/4 by 1/2. If I multiply them in that order, I'm going to get 3 over 8, right? Would it matter if I took the denominators here and switched them? Like if instead of that 4, I put a 2 and I put the 4 here. Still going to get 3 on top, still going to get 8 on bottom. So that's exactly what I did to those two fractions. It just makes more sense with numbers to us usually. Does that help? Okay. All right, last but not least, we do see pieces of the sine x over x on this one. But what is the first thing that we check for every time? Plug it in. Also, the sine x over x one is the limit as x approaches what number? This one is pi. What's the rule for? As x approaches, that has to be a 0 for you to use those special trig limits. It doesn't work for any other x value because there's not a problem with plugging in any other x value. So if I just immediately plugged in pi to this, that would be like doing the sine at pi squared over 2 times pi. Let's think back to our charts. What is the sine at pi? 0. If 0 is over 2 pi, what is our final answer? 0. 0 is okay as an answer. I will repeat that many times. 0 is okay on the top. It is not okay where? On the bottom. All right.